So I can show you how the path integral looks like in configuration space, which is exactly the expression that we derived in the last lecture, but it'll take 10 more minutes, and I'm just wondering if that's okay with you guys.
Yeah, it's fine, sir.
How about other people?
It's fine, sir.
Okay.
Okay, sir.
All right. So, right. Actually, I don't think it's going to take 10 minutes. It's going to take less. So to find the expression for the path integral in terms of Lagrangian, let me go back a few steps and write k again. So k small xn, x small n, tn, xn minus 1, tn minus 1 is equal to 1 over 2 pi h bar and dp, and we have established that for small delta t, we can exponentiate it. It's I by h bar. So, you can write Pn, but for now, I'm just going to ignore that because I'm just dealing with one. Delta t, and there's a p squared by 2m. This is the kinetic term. And then, there's another term which comes from the momentum eigenstates, which is px dot term. So I'm writing the px dot term now. This is the px dot term minus v of x. Okay. So now you see that I have a Gaussian integral with p squared, a quadratic term, and a linear term. And we know for complex Gaussian integral this interesting formula, which e to the power minus a of x squared. But if there's a linear term, say b plus b of x, what we can do is that we can, complete the square, which generates an extra term, which doesn't have an x dependence. And then we can change the integration variable, shift it, and then we can, again, use the Gaussian integration idea result. And then we get this result, e to the power b squared by 4a times square root of pi over a. So we can use this over in this integral. And what we have to do is that we have to identify a to be I by h bar, delta t by 2 of m, and b to be I by h bar, xn minus xn minus 1. And then if I do the integral, there are lots of constants that come in, and you have to be very careful, and you have to cross things out. And I'm not going to do this now. I'll leave it as an exercise, and it's also done in the notes. You will get x. When the dust settles, you get this formula. So this is a show. Okay. This becomes m by 2 pi I delta t h bar square root e to the power I by h bar delta t m by 2 xn minus 1 squared by delta t squared. So this is p squared. This is p squared. This is half mv squared and minus v of x. And then you can see that this gets rid of all because we have done the momentum integral. So now this expression for the propagator in the configuration space is because we have gotten rid of the momentum integral. Sorry. There should be x of 1, t of 1. This is going to be the limit in which n goes to infinity. And we have all these guys. How many of them do we have? We have n minus 1 of these. And then we have dxn minus 1 dot 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 dx2. And then we have the exponential of I over h integral from t1 to tn d of t, the Lagrangian classical of x and x dot. Okay, and this is what we have called the path integral. This is the measure, the Feynman measure. And let's just say this is the action as classical. And this is the derivation that we were looking for. Okay, so I have a few comments, but what I'll do is that I'll postpone the comments for the next time. Okay. Actually, let me just give you the comments right now. Okay. The comment that I wanted to make is that if you look at the position space path integral, what you have is you have the time direction there and the space direction here. Then you can have zigzaggy paths, right? As well as continuous paths. So even though, as well as smooth paths. So the path integral in configuration space is it's a continuous object. It may not be differentiable, it's continuous. But every time the trajectory changes in a non-differentiable way, what happens to the momentum? The momentum changes, suddenly. So if you look at the path integral on phase space, part of the integral will be over a discontinuous, range of momentum. Okay. So the integral there. So in phase space, so if it's p, so this is also part of phase space. The integral will be, suppose you start here and you go here, it'll jump around and it'll go a little bit and then it'll change and probably come here and then it'll come here and stuff like that. Well, it'll probably go in the forward time direction. So this is basically what I wanted to say. The comments. The last comment is that everything inside the path integral is classical. There are no operators. Inside the path integral, momentum operators, position operators, they've all been converted to their eigenvalues, and therefore they're all classical. Although the path integral itself is a quantum object because of the crazy paths that it takes, but everything inside there, these are all C numbers. There are no Q numbers there. Okay. And I think this is where I want to stop. And in the next class, I will derive the path integral for a system, for a simple system. Okay. Okay. Any questions? So who is missing today?
Shuja from there, I think.
Shuja, okay. All right. Any questions? Okay, so if not, I will see you guys Today is what, Monday, right? No, Sunday. I'll see you on Wednesday.
Thank you,
Thank
sir.
you, sir.
Okay. Bye.